We just watched a star die, not any star. One of the first stars that ever existed. A massive giant that exploded when the universe was only 730 million years old, before planets, before complex atoms, before anything we'd recognize as a solar system. And we caught it in the act, thanks to the most powerful telescope ever built. The James Webb Space Telescope just captured the death scream of something that died 13 billion years ago. The light has been traveling across the universe this entire time, and we finally heard it. This is the earliest supernova ever detected by humanity, and what it reveals about the universe's infancy will change everything you thought you knew about the cosmos. The discovery happened on March 14th, 2025. A space telescope called JWST detected something terrifying. A flash of gamma rays, high-energy radiation blasting across the universe. A gamma-ray burst, one of the most violent events in existence. Gamma-ray bursts are the universe's way of screaming. They happen when massive stars collapse, when their cores implode into black holes, when the star's outer layers explode outward in a supernova so bright it can outshine entire galaxies for weeks. This particular burst lasted about 10 seconds, which told astronomers something critical. This was a long-duration gamma-ray burst, the kind caused by a dying massive star. Not a collision, not a merger, a death. Within 90 minutes, NASA's Swift Observatory pinpointed the exact location in the sky. And then the real work began. Telescopes around the world turned their gaze toward that tiny patch of darkness, waiting, watching, hoping to see what came next. Because gamma-ray bursts fade fast. The initial flash disappears in seconds. But if you're lucky, if you're fast enough, you can catch the afterglow, the supernova itself, the expanding shell of dead star debris cooling as it spreads into space. If you want to witness the most groundbreaking discoveries in space science as they happen, subscribe now. Because what James Webb found will rewrite cosmology textbooks. The James Webb Space Telescope locked onto the target. Its massive golden mirror collected infrared light that has been stretched and reddened by the expansion of the universe itself. Light that left its source when the cosmos was in its infancy. And what Webb saw stunned the scientific community. A supernova, clear as day, designated SN in GRB 250314A. The explosion of a massive star 730 million years after the Big Bang. Let that sink in for a moment. The universe is 13.8 billion years old. This star died when the universe was only 5% of its current age. It exploded during the epoch of Ryanization, the era when the first stars and galaxies were just beginning to form. This is earlier than anyone expected to find a supernova. Earlier than most models predicted massive stars could even exist. We're witnessing stellar death from the cosmic dawn. Dr. Andrew Levin, the lead researcher from Radboud University, said something that captures the magnitude of this discovery perfectly. Only Webb could directly show that this light is from a supernova, a collapsing massive star. No other telescope in existence could have done this. Hubble couldn't see it. Ground-based observatories couldn't detect it. The James Webb Space Telescope, with its unprecedented infrared sensitivity, was the only instrument capable of catching this ancient light and proving what it was. But here's where it gets truly mind-bending. This discovery broke Webb's own previous record. The last time Webb found an ancient supernova, it was from 1.8 billion years after the Big Bang. This new one is more than twice as old, more than 1 billion years further back in time. We're not just pushing boundaries, we're shattering them. Every month, Webb reveals things that shouldn't exist yet. Galaxies too massive for their age. Black holes too large for the time available to grow them. And now supernovae from the era when the universe was still figuring out how to make stars. Subscribe to stay ahead of the discoveries that are forcing scientists to rewrite cosmic history. The research team wasn't just hunting for the supernova. They were searching for something even more elusive, the host galaxy. The galaxy where this star lived and died. Finding the galaxy was critical, because it tells us what conditions were like in the early universe. What kind of environment could produce massive stars capable of exploding as supernovae? What elements existed back then? How did the first galaxies form? And Webb delivered. For the first time ever for such a remote event, the telescope detected the host galaxy, a tiny faint smudge of light. So distant and dim it appears as just a few pixels in Webb's images. But those pixels tell a story spanning billions of years. The galaxy looks ancient and primitive, exactly what you'd expect from something forming in the early universe. But here's the shocking part. The supernova itself looks modern. Dr. Neil Tanvir from the University of Leicester explained it best. "We went in with open minds, and lo and behold, Webb showed that this supernova looks exactly like modern supernova. This shouldn't be possible. The early universe had different chemistry, less heavy elements, fewer of the metals that give stars their complexity. Stars back then should have behaved differently, exploded differently, created different kinds of supernovae, but this one matches what we see in nearby galaxies today. The light curves, the spectral signatures, the way it brightens and fades. All of it suggests that massive stars, 730 million years after the Big Bang, exploded the same way massive stars do right now in our cosmic neighborhood. That uniformity is both comforting and terrifying. Comforting because it suggests the laws of physics are truly universal, truly constant across time. But terrifying because it means we don't understand the early universe as well as we thought. If stars were exploding the same way back then, what else was happening that we've been wrong about? How quickly did the first generation of stars form? How fast did galaxies assemble? How soon after the Big Bang did the universe start producing the heavy elements necessary for planets and life? These are the questions keeping cosmologists awake at night, and James Webb is the only tool we have that can answer them. We're decoding the universe's earliest chapters. Subscribe to be here when we discover how stars like our sun became possible. Let me paint a picture of what this supernova represents. 730 million years after the Big Bang, the universe was dark, mostly empty, filled with neutral hydrogen gas. The first stars had only recently ignited. The first galaxies were just beginning to clump together. Into this cosmic nursery, a massive star was born, not like our sun, bigger, hotter, burning through its nuclear fuel at a reckless pace. It might have lived only a few million years, a cosmic eye blink. And when its core ran out of hydrogen to fuse, when the outward pressure of nuclear fusion could no longer support the star's immense weight, the core collapsed. In less than a second, it imploded into a black hole. The collapse released more energy than the star had radiated in its entire lifetime. The outer layers exploded outward at a significant fraction of the speed of light. The gamma ray burst shot across space in a tightly focused beam, and by sheer chance, that beam pointed directly at Earth. 13.1 billion years later, those gamma rays arrived, struck SVOM's detectors, triggered the alert, set off the cascade of observations that led to Webb's historic detection. We weren't watching the death in real time. We were watching a recording, a light echo from an event that happened before our solar system existed, before Earth formed, before anything in our local universe took its current shape. That star's death contributed to the chemical enrichment of the early universe. The explosion scattered heavy elements into space: carbon, oxygen, iron, silicon, the building blocks of planets and life. Future generations of stars would incorporate those elements, build worlds, create conditions where chemistry could become biology. The supernova you're learning about right now might have seeded the materials that eventually became you. That's not metaphor, that's cosmic genealogy. The team plans to observe this location again in 1 to 2 years. By then, the supernova light will have faded significantly. The galaxy will be easier to study without the overwhelming brightness of the explosion. They'll be able to measure the galaxy's properties precisely, confirm the supernova's contribution, understand what that early environment was really like, and they'll search for more. Because if Webb found one supernova from 730 million years after the Big Bang, there must be others. The universe is vast. The early universe was active. More massive stars were dying. More galaxies were forming. Each new discovery pushes back the frontier, shows us what the cosmos was capable of even in its infancy, forces us to confront how little we truly understand about the universe's history. This discovery wouldn't have been possible without international collaboration. SVOM detected the burst. Swift pinpointed the location. Ground-based telescopes tracked the afterglow. And Webb delivered the definitive proof. It's a reminder that modern astronomy is a team sport. No single nation, no single telescope, no single scientist can answer the biggest questions alone. We need the entire planetary community working together, sharing data, combining observations, pushing the boundaries of what's possible. Subscribe so you're here when the next impossible discovery forces us to rewrite what we thought we knew about the cosmos. But let's talk about what this means for you, for us, for humanity's place in the universe. This supernova died before our galaxy took its current form, before the sun ignited, before anything familiar existed. And yet its light finally reached us, connected us across unimaginable distances and timescales. Every photon Webb detected traveled for 13.1 billion years to reach that mirror, crossed the expanding universe, survived the cosmic journey, arrived at the exact moment when humanity had built a telescope capable of seeing it. That's not just science. That's philosophy. That's the universe telling us that we're connected to its earliest moments, that the atoms in our bodies were forged in supernovae just like this one, that we're made of star death and cosmic violence. It's humbling and it's empowering. Because if we can look back 13 billion years and watch stars die at the dawn of time, what else can we do? What other cosmic secrets will we uncover? How far will we push the boundaries of human knowledge? James Webb has only been operational for a few years, and it's already breaking records, finding impossible galaxies, detecting ancient supernovae, revealing exoplanet atmospheres, showing us the universe's infancy in unprecedented detail. Imagine what we'll discover over the next decade, the next century, as technology improves, as telescopes become more powerful, as we build observatories in space and on the moon and throughout the solar system. This is just the beginning. The cosmic dawn is revealing its secrets, and we're here to witness it. What do you think the earliest stars were like? Do you think the first generation of stars behaved differently than the ones we see exploding today? Share your thoughts in the comments below. The universe's first chapter is being written before our eyes, and thanks to James Webb, we're finally learning to read it.